Okay, here we can start. All right, okay. So we'll start now. So today I'm going to write on directly on these slides. So as usual, we'll go slowly. As usual, if you have questions, just speak up. It's a small class, so this should not cause any disruption. Oh, some people are still coming in. Okay, now we were talking about gradient flows in the Wasserstein space, and we have kind of given the introduction and the main theorems here. But it helps to understand how gradient flows are actually classically defined, especially on the Hilbert space. Okay, so we're going to talk today, go over slowly over the theory of gradient flows on Hilbert spaces and the kind of results that you can derive. And then by analogy, you can expect why similar things would hold for the Wasserstein space, although the analogy is not exactly sure because the Wasserstein space is not a Hilbert space, but the same kind of ideas and are going to the proofs. All right, okay. If you cannot hear me, if the audio drops at some point, just send a message in the chat and I will get to know. So let H be a Hilbert space. So the kind of Hilbert spaces that we have in mind, so would be that H would be, let's say, a finite dimensional Euclidean space. That would be one element of Hilbert space. Or for example, H would be L2 of dx. So this is the Lebesgue measure. So all the L2 functions of the Lebesgue measure. Or there are other kinds of Hilbert spaces that we'll consider. We'll see an example at the end of the class of a particular Hilbert space that we'll use these results for. But just for now, just think about H as some finite dimensional Euclidean space. And so I'm given H. Let phi be a function from H to R union infinity. Now, whenever I'm dealing with these infinite dimensional Hilbert spaces, I really, really need to specify this infinity. For finite dimensions too, sometimes we do it, but for infinite dimensions, this is absolutely critical that you consider functions that take value infinity, because most of the time, these functions are not going to be defined over let's say, the entire L2. It's only over some subspace that is going to be defined. So it's very important that you consider this to be with infinity. Now, given an initial vector given initial x0 in this Hilbert space H, say the following curve xt, this curve is a gradient flow of phi if it is a solution to the following initial value problem. Which is x dot t is equal to minus gradient of phi of xt for all t greater than or equal to 0. So that's my equation of gradient flow for Hilbert spaces. Now, there are several things that one needs to understand here. One is, what is x dot t? Now, x dot t is easy to define. This would be the limit as epsilon goes down to 0 of x of t plus epsilon minus x of t divided by epsilon. Now, because I'm working on a Hilbert space, The numerator, which is xt plus epsilon minus xt, is well defined because Hilbert spaces are linear, so this is well defined. And dividing by epsilon is well defined. Hilbert spaces are linear, so this is well defined. When I take this limit as epsilon goes to 0, what do I mean here? It is a limit in the Hilbert space norm, which means that the convergence is intrinsic to the Hilbert space. Okay, so this is a Hilbert space convergence. Okay, equality makes sense, equality. But the thing I should understand here, so that x dot t is an element in the Hilbert space itself. Because xt plus epsilon minus xt is in the Hilbert space. Divide by epsilon, it's in the Hilbert space. If I take a limit in the Hilbert space, it remains inside the Hilbert space. It's complete. It's closed. And so this actually is an element in the Hilbert space. Therefore, the right-hand side also has to be an element in the Hilbert space. And I'll come to this. I'll come to how to define the gradient of the function in the Hilbert space. But for now, I'll just take it for granted that there is a natural way you can define the gradient function on the Hilbert space. And just look into this equality, which is x dot t is equal to minus gradient of phi of xt. So if there is a solution of this equation, if there's a curve on the Hilbert space xt that solves this, and it starts from x0, we say that this is the gradient flow of the function phi starting from x0. Good, makes sense? So let's see some consequence before we define what is the gradient of phi. So we'll talk about how to define gradient of phi, but we'll talk about this later. So what are some consequences? One immediate consequence is the following. So one immediate consequence is the following, which is look into the time derivative of the function phi along the gradient flow curve xt. The idea behind gradient flow is that I'm trying to reach the minimizer of the function phi. So I should at least expect that the value of the function phi of t is going down as t is going to increasing. And so let's check that. So what is the derivative ddt of phi of xt? Well, by chain rule, I get that this is equal to gradient of phi of xt and then times xt dot. Now xt dot satisfies this is minus gradient of phi of xt. By the way, this dot means this is the Hilbert space inner product. So I will just write it that way. This is the inner product in the Hilbert space. And then by definition, this is equal to gradient of phi of xt minus gradient of phi of xt, which is minus norm square gradient of phi of xt. Good. So what we learn from here is one, that phi is indeed decreasing along xt. Why? Because the time derivative, this is clearly negative, or at least non-positive. Right? The Hilbert space, the norm square is always something that is positive. It is zero if and only if the vector is zero. Otherwise, it's always strictly positive. And therefore, the time derivative of the function along the curve of the gradient flow is non-negative, non-positive, and it's actually strictly positive, strictly negative, unless the gradient of phi is 0. Okay, so we learned that phi is decreasing along xt. So that's one. And two, and that's the other important thing, is that this time derivative of phi of xt, this is 0 if and only if xt is a critical point of phi. Right? So if time derivative is zero, then the norm square is zero. So if ddt of phi of xt is zero, then from here, this norm square, this term is going to be zero, which means that gradient of phi at xt must be zero. So then xt is a critical point. And conversely, the gradient of phi is zero, which would imply that the time derivative is zero. And this is the only possibility. Otherwise, it's strictly decreasing. And so one thing that it guarantees is that the function value is strictly decreasing along gradient flow. And it gets stuck only if you are at a local minimum or local, I mean, in this case, it has to be a local minimum. But there is no guarantee, of course, there's an absolute minimum of the function phi, although we are going to soon make assumptions on that. But at least we know that it has to get stuck in some kind of local minimum. It also points to this thing that no matter what notion of gradient of phi that we define, it must satisfy chain rule. There has to be some natural definition of a gradient which must satisfy the chain rule. Okay, otherwise this argument doesn't work. So let's see how to define gradient of phi. Are you guys okay so far? Okay, I know of a professor who was teaching an online class, and after the end of the class, he realized that his mic was off and nobody could hear him. So give me a sign. You guys are okay?
Yep, yep.
Okay. So let's go back to this question, how to define gradient of phi. So we first define a directional derivative, and we'll define gradient from there. So first define a directional derivative. So remember, everything holds true for Euclidean spaces as well. So there's nothing you should, if you want to have stronger intuition, just think about what I'm doing in the Euclidean space. So first define a directional derivative in the following way. So fix a point x and v in the Hilbert space. Let okay, why is this constant? Okay, let d phi of x in the direction of v be defined in the following way. This is the limit as epsilon goes to 0 of phi of this ratio. So phi of x plus epsilon v minus phi of x divided by epsilon. Sometimes you hear the word Gatto derivative. This is similar to that. So it's a Gatto derivative. But what this is really saying is that you draw this line. So you have x here, and you draw this line of x plus epsilon v. So you draw the line in the direction of v, and along that line, you take the derivative of the function phi with respect to epsilon. This one single parameter. Okay. Now assume that this exists for every v. Exists for all v for a given x. If it exists for all v for a given x, actually you can show that this has to be a linear function of v. Assume this is a linear and a continuous function of v. Linear continuous function. of V. This is, of course, real valued. And so what I'm assuming is that for every given x, I have a linear continuous function over the Hilbert space. Thus, for a given x, I have a linear continuous function d phi x from the Hilbert space to the real line. But because I'm working on a Hilbert space, all such linear continuous functions must be given by an inner product with respect to some element in the Hilbert space. That's a Riesz representation theorem. So by the Riesz representation theorem, there exists some function, some vector that I'm going to call gradient of phi of x in the Hilbert space H, such that d phi of x in the direction of v, this is equal to the inner product of gradient of phi of x and v. And this inner product is the Hilbert space inner product. Okay. So assuming that this directional derivative exists, you can actually always show very easily that this is linear. Assume that this is actually linear and continuous function of v. Then for every fixed x, you have a linear continuous function on the Hilbert space. Therefore, it is given by an inner product. And take that element with respect to which you are taking the inner product, and that's what you define as a gradient of phi of x. Okay. This defines uniquely gradient of phi of x as an element of H. And from here, you can show that this satisfies chain rule. Good. So this is the way you make sense of the gradient of a function over a Hilbert space, which satisfies chain rule. And once you have this, then again, this problem now makes sense. I'm talking about a curve in the Hilbert space. I'm talking about a curve in the Hilbert space where x dot t is minus the gradient of phi of xt. And any such curve, when starting from x0, must satisfy that the function is decreasing along the curve. And the only way it can get stuck is if I have reached a critical point of phi. Okay. All right. Good so far? Any questions? Okay, so the next question we ask is, when does a gradient flow exist and when is it unique? When does gradient flow curves exist and is unique? So when can I say that the solution x dot t is minus gradient of phi of xt? This actually exists, and x0 is given. And so, and given x0, when can I say that the solution actually exists and is as unique? We need some conditions for that. Now, in Euclidean spaces, even also in Hilbert spaces, there is one easy way to construct the solution. So, solution can be constructed by Picard iterations when the function that takes x to gradient of phi of x is Lipschitz continuous. Now, this is a very, very strong assumption. So I'm looking into x to gradient of phi of x as Lipschitz continuous, which is effectively saying that the Hessian of phi is bounded. A very, very strong condition. So most of the time it doesn't really work. But let's just see when the conditions are super nice, when I can actually do this, how is it done? So how is this done? The Picard iteration. This is my standard Picard iteration. I'm just going to write down the formula in case you have not seen this before. And so how is this done? Is that you start from an initial curve x0t, and now you define iteratively xk plus 1 t to be x0 plus, or rather minus, 0 to t gradient of phi of xks ds. Right? Um, Clearly, this is a scheme whose fixed point is going to give me the gradient flow. Right? This is the integral form of the gradient flow. Right? The gradient flow curve is going to be a fixed point of this iteration. Or it is a fixed point of this iteration of this scheme. And so you can believe, and it's not particularly hard to prove, that this scheme will indeed converge and will converge to this unique curve, which is this gradient flow curve, under my assumption that x to gradient of phi of x is Lipschitz. So fact, when x to gradient of phi of x is Lipschitz, these iterations converge to a limiting curve, to a limiting curve that satisfies the gradient flow ODE. Moreover, this curve is unique. Good. This all seems very good because, I actually have the curve. I can actually construct it by this Picard iteration. The bad thing is that over infinite dimensional spaces, even over Euclidean spaces, you would be hard-pressed to find a function such that its gradient of phi is actually Lipschitz. So that's going to be the hard part. Most of your functions that you will actually see is not going to satisfy your assumption. So the con is that the assumption is too strong. Okay. Okay. So because this assumption is too strong, we have to come up with alternate ways in order to construct this gradient flow curve. And we'll show these alternate ways. These are the Euler iterations, also something that we have mentioned before, but let's see how they perform over Hilbert spaces. So alternate ways to construct this by discretization. Alternate ways to construct solutions is via Euler iterations. So what is Euler iteration? Euler iteration is a time discretization of this flow where we construct a sequence of points which approximately satisfies this gradient flow equation. And we take a limit of this sequence and see if such a limit exists, and this limit satisfies the ODE. So to construct all our iterations, we fix a time step tau, and define a sequence xk tau by, so x tau 0 is x0, and x tau k plus 1 minus x tau k divided by tau is equal to minus gradient of phi of y for some suitable y. All right. So you pick some, you are discretizing the time derivative by discrete derivative. And what is the discrete derivative? X tau k plus 1 minus x tau k over tau. On the right-hand side, you're also you have a choice to pick where do you evaluate the gradient. And so for different choices of y, you get a different discretization of this gradient flow curve if it exists. We are trying to construct the curve. So two popular choices of y are: one, the explicit Euler scheme, which is where I take y to be x tau k. Or the other choice is the implicit Euler scheme, where y is x tau k plus 1. You can see why these are named so, because if I take y to be x tau k over here in this equation, then I can solve for x tau k plus 1 purely in terms of x tau k. For the implicit one, this becomes an implicit equation. I don't have a closed form solution of x tau k plus 1, but it gives me some way to proceed if I can essentially solve that implicit problem. I should mention that there are other choices of y. And some of these methods actually work better in different scenarios. For example, I could look at the midpoint between the two. For example, I could look into some randomized way of picking a point y between x tau k and x tau plus 1. There are multiple ways this goes into different numerical schemes, but we'll be essentially looking into two, which is implicit Euler scheme. All right, good. You might ask, why do we look into implicit Euler scheme when the explicit Euler scheme is clearly more intuitive and better? Like, because it's explicit and I can easily converge. So I'll try to convince you by giving an example where you will see that the explicit Euler scheme does not converge to the gradient flow curve. All right. So here is an example of the explicit Euler scheme not converging. Explicit Euler scheme may fail to converge. I haven't really said what do I mean by convergence. What am I actually looking for? What I'm looking for is this. So goal is as tau goes to 0, I want my xk tau in some sense to converge to xt, a curve, which satisfies the gradient flow ODE. That's really what I'm looking for. I'm looking for the sequence to converge in some way to a curve, where the curve will satisfy the ODE of gradient flow. That's my goal. So I'll give an example to show that the explicit scheme may actually fail to converge. Are you good? Are you good so far? Any questions? All right, okay. So the explicit Euler scheme may fail to converge. So here's an example. So let's take my Hilbert space to be this a real line. Okay, as simple as possible. And I'm going to take my function phi to be 3 over 4 x to the power 4 over 3 when x is non-negative, and infinity when x is negative. All right. Where is this function minimized? This function is clearly minimized at x equals to 0. This function is minimized at x star is equal to 0. This is in fact unique. Now let's start my gradient flow from x0 equals to 1. Consider the gradient flow starting at x0 is equal to 1. So I have to compute what is the gradient of this function. So inside its domain, the gradient is well defined because this is a smooth function, except for x equals to 0, as we'll see. And what is the gradient of phi of x? The gradient of phi of x is equal to, so 3 over 4 times 4 over 3, and this is just phi prime of x, by the way, x to the power 1/3. So it's just x to the power 1/3. So I'm looking for a solution of the following ODE, where xt dot is equal to minus x to the power xt to the power 1/3, starting from x0 equals to 1. Good. You can explicitly solve for this. This is this is not a difficult ODE to solve. And you can see that the solution is given by xt, which is equal to 1 minus 2t over 3 raised to the power of 3 over 2. Right. Just verify that this is actually a solution. What happens if I take xt dot? The 3 over 2 in the index becomes 1/2. I will get a minus sign from the minus 2/3. 3 over 2 will cancel with 2/3 sitting in front of t, and I have xt to the power 1/3. Good. Everybody's following this? So xt equals to 1 minus 2 over 3, 2t over 3 to the power 3/2 is a solution, is a gradient flow solution, starting when x0 equals to 1. Now observe something very special about this gradient flow curve. It actually attains its minimum, which is 0, exactly at t equals to 3 over 2. It's not particularly important for what I'm telling, but it's an interesting characteristic here. So at t is equal to 3 over 2, the curve attains the minimum. Okay. Sorry for this noise outside. Do you see this? Do you understand what I'm saying? So t equals to 3 over 2, 2t over 3 is 1, 1 minus 1 is 0. Okay. Now, if I want to discretize this according to my Euler scheme, my explicit Euler scheme, what will I get? So I want to discretize this, so fix some tau, which is strictly positive, and then my explicit Euler is going to give me x tau k plus 1, which is equal to x tau k minus tau times the gradient of the function at x tau k, which is x tau k to the power 1/3. Okay, I can start with 0. Sorry, 0, starting at 1. Okay, now I want you to tell me why this discretization scheme cannot converge to the minimum no matter what tau is. Can anyone tell me why? Look at the curve. This is my gradient flow solution. Look at the discretization. Tell me why this can never converge to the curve as tau goes down to 0. No matter how small your tau take, this cannot converge.
What do you mean by converge? Does it have to attain it, or can it just be very close?
Right, so what do I even mean by converge? So let's maybe write down. So what do I even mean by converge? This is a good question. So the way that typically this convergences will work is that, so given a discretization scheme, so given a discrete sequence, x tau k, make it continuous. So do a continuous time interpolation, which is x tau t is equal to x tau k when t is in k times tau and k plus 1 times tau. So you basically do a piecewise continuous curve. So you divide your time in pieces of tau, 2 tau, 3 tau, and so on. And you do a piecewise continuous curve. Piecewise constant, in fact, curve. And that's your x tau t. And then you ask, like, is there a curve? So is there a limit to, take limit, tau going to 0 of x tau t? You can also ask whether this limit is uniform in time, uniform over compact sets of time, but that's a basic idea. That you shrink your time into blocks of tau, and then you take a limit, and then you ask whether this actually has a limit.
I think
That's
in
just,
this case, yeah,
yeah.
thank you. I think in this case, as it gets closer and closer to 0,
Mm-hmm.
in the neighborhood of tau, tau
Mm-hmm.
is kind of bigger.
Yes.
or sort of too small. So the third power makes it grow relative to tau, and then
Mhm.
maybe it might oscillate or something, and it can't get closer than because tau is fixed and finite,
This is
something
exactly
like that.
true. That's exactly what will happen because, well, my function value, in fact, is going to, as x star, I'm starting from 1. So in the very next step, I'm inside between the time 0 and 1. And once I'm getting into closer to 0 from the positive side, the third power is actually much bigger than x tau itself, x tau k itself. And so sooner or later, you will be on the left-hand side of the origin, which is outside the domain of this function, and the whole scheme breaks down, right? Even if I don't care of the domain of the function exactly what Geoffrey is saying, it will oscillate. There is no way this is going to converge to this point. But that's a problem. This is a typical problem of explicit Euler iterations. First of all, very good. Second of all, do you guys understand what the problem of this scheme is? Do the rest of you follow why this scheme cannot work here? It cannot work because as x tau k is getting closer to 0, x tau k to the power 1/3 is becoming much bigger than x tau k. And either you're going to go outside the domain or you're just going to oscillate. So this cannot converge. The fact that your explicit Euler scheme does not respect the domain of the function is a major problem in applications. That if you follow your explicit Euler scheme, you can land outside the domain of your function, and then that's it. Your scheme basically breaks down. And that's one of the major problems. And you see this very clearly in this example. Are the rest of you okay? Do you follow what I'm saying? Okay. Um, So this is why when people you don't actually want to use explicit Euler scheme, so use the implicit scheme. Sorry about this awful noise outside. Now to run the implicit scheme, how do we actually run this implicit scheme? One of the other good things about the implicit scheme is that there is a variation of formulation of the scheme, which does not even require the concept of derivative. So variational representation or formulation of the implicit scheme. So what is the implicit scheme? So recall the implicit scheme is given by minus the gradient of phi of x tau k plus 1. This is my implicit scheme. You can write this alternatively. I can say that x tau k plus 1 is the argmin in x in the Hilbert space. I've already explained this last time why this scheme actually works, because if you take derivative inside and if you write down the first order condition, then this is the first order condition for this problem. This is the first order condition for this optimization problem. It gives you back the explicit Euler scheme. But notice here that gradient of phi is not even needed. You can purely define the next step of the implicit Euler scheme by an optimization. You don't need to define gradient. Gradient may not even exist. And that's one of the main reasons why people really like it when you're doing infinite dimensional problems, because where defining gradients is always tricky. So an immediate benefit of this is that I can now define um, my gradient flows to subdifferentials of convex functions. So immediate benefit, may be defined
Do you mean to
to,
go back to your point about it's hard to define the gradient because we would have
yeah.
to look at that inner product and we can't work it out, we can't compute it, or we can't work something out symbolically. Um,
Well, yes. I mean, yeah, I mean, exactly. I mean, look at the case of the convex functions that I'm going to write down now. There are plenty of convex functions which have corners. So they don't actually have gradients at those points. So in a Euclidean space, our convex functions need not be smooth. They are smooth almost everywhere, but they're not always smooth. And so what happens if you hit one of those corners? How do you move from there?
okay.
So we need, when we talk about gradients, we need to essentially make sure that the function is differentiable. And this differentiability of functions is not always guaranteed, especially when you're working with arbitrary Hilbert spaces.
Okay.
So gradient flows may be defined for convex functions, subdifferentials. So let phi on the Hilbert space. So let phi, this is my same function on the Hilbert space to the real line plus infinity, be convex. As usual, I have to define lower semi-continuous and proper. Now, once I define this as convex, lower semi-continuous, and proper, I always know that there are subdifferentials. So recall, y is a subdifferential of phi at a point x.
I'm not sure which message you're trying to unsend.
So recall that y is a subdifferential of a function at x if it satisfies that phi of z is greater than or equal to phi of x plus y z minus x for all z. Okay, so that's a subdifferential of a convex function. So phi of z is greater than or equal to phi of x plus y z minus x for all z. So these subdifferentials always exist. They will form some non-empty convex set. They will exist inside this domain, and these are much easier to work with when you're dealing with infinite dimensional spaces, but also convex functions in finite dimensional spaces. And so define gradient flow of phi as any solution of the ODE where you now write x dot t is an element in the subdifferential of the function phi at xt. So gradients don't need to exist. All you really have to assume that x dot t is inside the subdifferential of gradient of phi at xt. The fact is if phi is convex, lower semi-continuous, proper, the implicit Euler scheme will converge and will give you a solution of this ODE. The implicit scheme converges to a solution of this ODE. Okay, so you can construct a solution of this ODE if by this implicit Euler scheme. There are several nice things that happen to this gradient flow curve when your function phi is convex. One of them is uniqueness. So I'll write down a one-line argument of why this gradient flow curve must be unique when you're considering a function that is convex. Okay. Uniqueness is easy. You guys are still following what I'm saying? Okay, so what do I mean by uniqueness? So what I mean by uniqueness is that if I look into a solution of the ODE, starting from a single point x0, then xt for any future time t is uniquely defined. That's what I mean by uniqueness. To see this uniqueness, start two gradient flows. One is xt dot. This is in the subdifferential of phi of xt with initial point x0. And the other is yt dot, which is in the subdifferential of the function of yt, and this is starting from y0. So I have two different curves, which are both gradient flow curves, starting from two different points, initial points. Now look into the time derivative of xt minus yt norm square. Now, if I have a convex function, if I have, let's say, a strongly convex function, then it has a unique minimum. And so if I have a unique minimum, you would expect that these curve xt and yt are both converging to the same unique minimum, so they should get closer and closer to each other. And let's see if this is true. So I have xt minus yt norm squared. If I take the time derivative of this, I would get by chain rule, I would get this is 2 times inner product of xt minus yt and time derivative of xt minus time derivative of yt. And so this is equal to 2 inner product of xt minus yt. What is xt dot? Well, xt dot is some element. This should be minus, by the way. Okay. Okay, none of you spotted this problem, but of course it has to be a negative of this because otherwise it doesn't work. I'm doing a gradient flow, so xt dot is negative of the gradient. So I'm in time, I'm negative of this, and so xt dot is some element in negative, some element in this set. This is an abuse of notation because this is really a set, which is del phi of xt. I'm just writing it as an abuse of notation here. And then I have yt, which is plus some element in the subdifferential of yt. Again, I want to stress that this is an abuse of notation. Del phi is actually a set. Nevertheless, what I get is negative 2 xt minus yt and del phi some element in the subdifferential of xt minus some element in the subdifferential of yt. Now I claim that this quantity is always less than or equal to 0. Why? What property am I using here to claim that this element this inner product must be less than or equal to 0? So this is a question to the audience. Why is this inner product less than or equal to 0?
Monotonicity of subdifferential.
Very good. It's the monotonicity of subdifferential. So recall, if I have this is exactly correct. This is the monotonicity of subdifferentials. So if I have any element p in the subdifferential of phi of x, any element q in the subdifferential of phi of y, then inner product of p minus q with x minus y, this is greater than or equal to 0. In fact, this is strictly positive if phi is strictly convex. How do you prove this? Take both the curves, take the two equations where the curve is lying above the tangent at x, curve is lying above the tangent at y, and add the two up. And you add the two up, you get this. So this is when I'm actually using convexity. I'm using convexity to say that the subdifferentials have monotonicity, and therefore this inner product over here, as we see, this is non-negative. And this is strictly negative as long as phi is strictly convex. And so what I see from here is that norm of xt minus yt is strictly decreasing if sorry, okay, is strictly decreasing if phi is strictly convex. All right. Where can it decrease to? The only point where it can decrease where this is actually going to be equal to 0. And that's where you have converged to the unique minimum of this strictly convex function. Okay, now go back to uniqueness. So I want to prove that the gradient flow curve is unique as long as this function is convex. The function phi is convex. How do I see uniqueness? I will take both x0 and y0 to be equal to each other. If I take x0 and y0 to be equal to each other, then x0 minus y0 norm square is 0. Because xt minus yt norm square has to be less than or equal to x0 minus y0 norm square. That also remains 0 forever. And therefore, given an initial point, I have a unique curve. So the argument for uniqueness take x0 is equal to 0, equals to y0. Thus, initial difference, x0 minus y0 norm square, this is 0. By monotonicity, xt minus yt, this norm square, which is less than or equal to x0 minus y0 norm square, must also be 0, but this is of course non-negative. And this implies that xt is equal to yt for all t. This gives me uniqueness. Good. This argument you can actually show also works for all semi-convex functions. I will leave it to you to verify this argument actually also works for semi-convex functions because by an judicious use of Gronholz inequality, but I'll leave it for you to verify. So as long as your function is semi-convex, you can get to its solution by using the implicit Euler scheme, and the solution is going to be unique. Everybody good so far? So now we go to convergence. Any questions on this? Are you following this? Let's go to convergence. Convergence rate for gradient flows. Now, to get to convergence rates of gradient flows, we are going to assume what is called a PL condition. So say the function phi the PL condition, this is the Polyak-Lower-Civitz condition. I want to make sure that don't make a mistake here in spelling. Polyak condition with a constant C if the following happens. If, so this constant is positive, if for all x, in the Hilbert space, I have the following inequality, which is 1/2 norm of phi x square is greater than or equal to c times phi x minus phi of x star norm square. This says to phi x minus phi of x star, where x star is the minimizer of phi assumed to be unique. Okay, so this is comparing the value of the function from its minimum value with the gradient of the function. So the function could be like this, and I'm looking into, this is where my function is minimized, my x star. For any other point, I'm looking into this difference of phi x and phi star, and I'm comparing this with the gradient at this point. This is what it's doing, the norm square of the gradient. Good. There are generalizations of this condition, but this is a standard PL condition that we're going to work with. So the first fact is that the PL condition implies exponential convergence. So fact 1, if phi satisfies the PL condition or PL inequality, then starting from any x naught, the gradient flow curve converges exponentially fast to x star. So that's fact 1. And fact 2 is also what we will prove. If phi is uniformly convex, so lambda convex with some lambda positive, let's just use this term. Is lambda convex for some lambda positive, then it satisfies PL. So recall that lambda convexity means that phi of z is greater than or equal to phi of x plus, so del phi of x z minus x plus lambda over 2 norm of z minus x square. Okay, so I have a lower bound on the Hessian of phi. So these are the two facts that are important for us. If it satisfies PL inequality, then it converges exponentially fast. And if I have a lambda convex function, then it satisfies PL inequality. Let's try to prove this because the proofs of both of these are easy. All right, okay. So why does PL, so let's prove fact one. All right, okay. So let's see the proof of fact one. So I have my gradient flow curve, which is x dot t, is equal to minus gradient of phi of xt. And now look into ddt of phi of xt. So we did this in the beginning of the class. And this tells me that this is equal to gradient of phi of xt dot, and that's negative gradient of phi of xt norm square. At this point, I apply the PL inequality. And I get that so what was the PL inequality? So it's over here, that the gradient of phi of x norm square is greater than or equal to twice c phi of x minus phi of x star. That was the PL inequality. And so what I get from here is that ddt of phi of xt is less than or equal to negative twice c phi of xt minus phi of x star. Good. So let's assume without loss of generality that phi of x star is 0. Okay, it doesn't matter because I can always shift things up. So assume without loss of generality that phi of x star is 0. Then what I have here is ddt of phi of xt is less than or equal to negative twice c phi of xt. So obviously, what I will do here is apply Ground-Walls inequality. So I'm going to apply Ground-Walls inequality. To see that phi of xt must be less than or equal to phi of x0 and then e to the power minus twice ct. And this gives me exponential convergence. Convergence to 0 at rate twice c.
What do we do if what is C if
So
there's
C
more
is,
than one minimizer? How do we,
the PL inequality assumes there's a unique minimizer. It doesn't work if you have other minimizers.
okay.
I mean, unless you can show that your curve is contained inside a certain region where you don't escape, which has a unique minimizer.
Mm-hmm.
Okay. So PL inequality with a constant c implies exponential convergence at rate twice c. So this is true for all functions with the Hilbert spaces. The second fact, as I said, is that uniformly convex functions satisfies PL inequalities. So fact 2, proof of fact 2. So suppose phi is a lambda convex. What's not lambda strictly positive? Now, if I take, so what does that mean if I have lambda convexity? So it would mean that let's draw the tangent at the point x star. So at the point x star, by lambda convexity, I get that f of x, sorry, phi of x at phi of x minus phi of x star, this is greater than or equal to sorry. I would take the at x, not at x star. At x, and then I'll apply this to x star. So I would get that phi of x star, this is greater than or equal to phi of x plus gradient of phi of x. I'm using gradient, but okay, the argument works equally well for all subdifferentials. X star minus x plus lambda over 2 x minus x star norm square. All right, okay. So from there I get that phi of x minus phi of x star, this is less than or equal to gradient of phi of x minus x star minus lambda over 2 norm of x minus x star norm square. Well, I didn't do anything, I just rearranged terms. Took the inner product on the left-hand side, changed the sign, and so on. That's what I'm doing here. Now I'm going to use Young's inequality. So what is the Young's inequality here? Young's inequality, and I will leave it for you to verify that this is always true over a Hilbert space, that this is less than or equal to 1 over 2 alpha norm square A plus alpha over 2 norm square B for any alpha positive. Any alpha positive. So verify that this Young's inequality is always true. For alpha equals to 1, I'm sure you can prove this. And then for any other positive alpha, this is basically the same argument. And I'm going to use this Young's inequality for this middle term. And so I get phi x minus phi of x star. This is less than or equal to 1 over 2 lambda phi of x norm square plus lambda over 2 norm of x minus x star square. And then I have a minus lambda over 2 norm of x minus x star square. This clearly cancels out. And the remaining part is my PL inequality. Right? So just drawing the tangent at an arbitrary x and looking at what happens at the minimum x star, and some use of Young's inequality tells me that PL inequality must be true. So what I get from here is that all lambda convex functions must satisfy PL inequality. I want to stress here that lambda convexity is actually much stronger than PL inequality. And there are functions which are not lambda convex that can satisfy PL inequality. So lambda convexity is stronger. And the way to see that this is stronger is to go back here. Go back to this argument that we had done. At what rate is this function ddt of xt minus yt norm square is actually converging? If this is lambda convex, if function phi is lambda convex, then I actually have a control over this inner product, because this inner product will be lambda times norm square xt minus yt. So what we get from here is that if it is lambda convex, then I would get that d dt of norm square xt minus yt norm square is less than or equal to minus lambda norm square xt minus yt. And this would tell me that xt minus yt norm square is actually less than or equal to x0 minus y0 norm square e to the power minus lambda t. And so how do I see lambda convexity stronger? That any two curves, any two gradient flow curves are converging exponentially fast. But PL inequality only tells me that the convergence to the minimum is exponentially fast. Okay, so there's a fixed point, x star, to which I'm converging exponentially fast. So lambda convexity is saying any two curves are converging exponentially fast, which is much stronger because you can take the stationary curve and that will be exponentially fast, than the PL inequality, which is just saying, talking about converging to the unique minimizer. Okay, we'll stop here, but I hope this was clear. If you have any questions, please ask me now.
Since lambda convexity is so strong, how are we ever able to find the lambda or show that something satisfies lambda convexity? Or is it
Right.
usually just like a construct that we start from in proofs?
Right. So of course, so like the reason why I'm doing all this is because on the Wasserstein space, essentially the same ideas transfer. In the Wasserstein's case, if you have a log concave measure and you're looking into the gradient flow for the relative entropy with respect to a log concave measure, then that is exactly my lambda convex function. So if the log concave function is strictly log concave with lambda, then your corresponding Kullback-Leibler is a lambda convex function. And then essentially all this argument just goes through the Wasserstein space, although I'm not going to prove this because the proofs are more intricate. So yes, it is true that log concave functions or uniformly log concave functions are very special. And most of the things are not uniformly log concave functions. On the other hand, they are also the functions for which we can say a lot, and people often use them in modeling because outside of it, it's a jungle and you really can't say much.
So you can set up a model that, by a model, do you mean like that would be used in an inverse problem? You could set up a model and there's some guarantees that your model structure, there's a log concave function.
I would say that most of the time, at least in terms of modeling, if I'm trying to model something nice, I prove a theorem. People will first prove the theorem for log concave measures. Then they will say if there is perturbations of log concave measures and the perturbation is not too bad, then the theorem also continues to hold. And if your theorem is actually robust, then maybe you don't need log concave, but log semi-concave is enough. So some kind of semi-convexity bound is enough. So you allow some concavity, but you allow that the Hessian has a lower bound, and then maybe that's fine too. But in the gradient flow case, you can easily come up with examples of functions that are not uniformly convex, or maybe even semi-concave, but not uniformly convex, where the gradient flow curves don't converge. And so you cannot have a uniform theory for that. It has to be done case by case. Okay. Any other questions? Okay, so this was the introduction to all the Hilbert space. Next class, we'll go back to the Wasserstein space. Essentially the same theorems will continue to hold, but it's good to know that these theorems are exact for a Hilbert space. All right. If there are no other questions, then I'll see you guys on Wednesday. Take care now. Bye-bye.